Okay, we made it. So we are talking about hypothesis testing. And we did the, just like with confidence intervals, the first thing we look at is when the sigma, when the population standard deviation is known. Okay, because it's a place to start. Okay, it's a place to start. It's not probably the most ideal situation, because if you just took a sample of some data, you wouldn't necessarily know that. You probably wouldn't know that. Okay, the population standard deviation, but it's just a place to start. Okay, so let's look at that example again. So because I want to talk more about this example. So remember, this was where we left off. Can he hit his tee shot and average 275 yards? He claims he can. His friend says, no, you can't do that. So he hits 25 drives, and he gets a mean, a sample mean of 264.4. Okay, you got a sample mean of 264.4, and standard deviation of the population, 20 yards. And we want to make a conclusion at the 5% significance level. In other words, alpha equals 0.5, 5% chance of a type 1 error. Okay, so that was the setup. And here's when we're doing a hypothesis test, here's the approach. Okay, we're going to state the null and alternative hypotheses always. Then we're going to, just make sure we understand what we're trying to do. Let's discuss the logic. We're going to obtain the precise criterion for deciding whether to reject the null hypothesis. And so that means finding the z-score of the sampling distribution, right? Finding the z-score of the sampling distribution, and we're going to compare it to the z-score for our significance level, right? So we're going to find the z-score for the sampling distribution, which is going to give us an indication of, of the mean, but then where that sample falls, and then a z-score for the significance level, and compare those. Okay, and then we have, so our significance level was 0.05 or 5%. And so if that z-score lies down here, well, there's only a 5% chance that it really should have been over here. But then like a 95% chance that it was indeed that far away from the mean. So we're going to reject, so that the z-score for the significance level gives us that boundary, we compare it to that to say whether we're going to reject or not reject. Okay, so for z alpha of 0.05, we saw that z-score was negative 1.645 standard deviations below the mean. Okay, and so let's just set up the z-score again. So how do we find a z-score for a sampling distribution when this population standard deviation is known? Okay, so how do we do that? So we're testing it against 275, right? So our null hypothesis was that he can drive it 275 yards. Alternative hypothesis, his friend says, no, you can't. And so the implication there was your true mean driving distance is less than 275. Okay, and so how do we set this up? Remember, our z-score is how far away we are from the mean, normalized into a number of standard deviations. So how far are we away from this hypothesized value? So we'll do 264.4 minus 275. So that's how many yards his average of the sample was below the average he claims. But then we want, remember, z is the number of standard deviations. So we're going to divide by 20. and then per a sample 25, we're going to divide by square root of 25. Okay, and what do we get for that z-score? Negative 2 something, right? 6.5? So if his mean driving average was 275, then this sample lies negative 2.65 standard deviations below the mean. And so we're saying if his driving distance was 275, then, yeah, like I said, this particular sample was way low compared to that. So at a 5% significance level, we would reject this, right? Because 2.65 is over here. So less than 5% of the time, if his driving distance was 275, then less than 5% of the time, we would get a sample like this. But let's take this a step further and say, exactly what percent of the time would we expect a sample less than this? So how would we find this? So if we want to know exactly what percent of the time his sample would be this number of standard deviations or less, in other words, so we set the significant level at 5%, but then we got this z-score. Well, that indicates a certain percent of the time as well. So how would we find that? So what percent of the time would he hit, would he have a sample of 25 that was less than 264.4? So what percent of the time would he hit a sample of 25 drives that had a mean of less than 264 if his actual mean was 275? How would you figure it out? Yes, so now go back to the table, and we're going to, this is an old question from like a month ago or 3 weeks ago. What's the probability if his mean was 275 that he hit 25 drives and get an average on those 25 of less than 264.4? Right, this is just a basic sampling distribution question, right? When we did this a couple of weeks ago. So, what is that? What is it? She found 1.4%. Somebody else get that? Or 0.4%? 0.4%. So it was 0.0004? So 0.4%. So from the table, you get 0.004. That's 0.4%. This was 5%. So we were checking it against a 5% confidence, but really what his z-score indicated was if he drives at 275 on average, then this sample would, or something less than this, would occur less than 1% of the time. So it's not only did we not make the 5% confidence level, but this is great evidence to reject the null hypothesis that no, he doesn't drive at 275, because this one sample, if he does drive at 275, a sample like this would happen less than 1% of the time. You see? And our standard was just something like 5%. So this thing right here is called the p-score. The p-score is the percent corresponding to the calculated z-score. Okay? So even if we started this hypothesis test and say we want a 1% significance level, if we want a 1%, well, that would be here. we still would reject at a 1% confidence interval based on this p-score. So a p-score is a way to say, it's kind of like doing it the other way. Rather than starting with a confidence level and then comparing your z-score to that, it's like, let's find what the probability of this sample would be if you had that mean, and then we'll say to what degree of significance does that indicate, right? So even if we started with a 1% significance level, we still would have rejected based on the z-score that we got. Okay. So z's are comparing with z's, right? We're gonna get a z for our significance level. We compare that to the z, and then the significance level compares with a p-score, right? Because those are probabilities. So this 0.4%, we compare that to 0.05, and then this critical value of negative 1.645, we compare that to the z that we calculated. So conclusion, no way, right? So very, very, very unlikely that he truly drives a 275 and he just had happened to have a really, really bad sample. That only happened less than 0.5% of the time. Okay? So definitely, we would even reject it at the 1% significance level. Okay, does that make sense? So that's the idea of a p-score. Okay, and so just to point out, when you have a significance level and you're doing a two-tailed test, meaning we're just testing to see whether you're different from the hypothesis, not necessarily less or greater, but just different, then whatever your significance level is, you have to put half of that on the left tail and half of that on the right tail. Okay, so if we wanted to do a two-tailed 1% significance, tell me what the z-scores would be for a two-tailed 1% significance. What are you going to look for? What area is this right here? No, but before you look at the chart, what area are we going to have right there? 0.05. So remember, 1% is 0.01. So what area, if we're going to 1% significance on a two-tailed test, then what area are we looking for here? 0.005. And then this will also be 0.005 on this side. So tell me what the z-score will be for a two-tailed test with 1% significance. Go find that. So what are you going to look in the table for? You got two choices, right? There's two different ways you could find that in the table. He said 2.575. Miguel likes it. Whitney likes it. Okay, cool. So this then z for that would be 2.575. So if our z-score, if with a z-score for a certain hypothesis test was greater than that or less than the opposite, negative 2.575, we would reject. We would reject. Okay. Any questions on that? So don't try to write all this down. This is just kind of a summary of the z-test. The z-test for a hypothesis test. We have a simple random sample, normal population or a large sample. When the population standard deviation is known, and then we we're going to set up our null hypothesis, which is always, the null hypothesis for us is always, is the population mean a certain value? Okay, and then there's three possible alternatives to that. It's just not that value, so it could be too high or too low. It's less than that value, or it's greater than that value. We decide on a significance level. We compute the value of the test statistic, or the z-score for the sampling distribution. Okay, and then we compare it. So we're going to find the critical values, and then we're going to do our comparison. And so we've seen that, so let's do another example. Okay, why don't you give it a shot? So let's, how many? Two there. I think we can fit five. Yeah, we can fit in five on the sheet. So let's go ahead and do this on the sheet. Okay, and whenever, so a couple things. When you work on it, make sure you work up and down like this. Up and down like this. And I need name and date. Upper right-hand corner, please. Not upper left. Upper right-hand corner. And work up this way. Anybody else need one? What's the date today? 18. Right? Yeah, 18. Okay, so you can work together, of course. And whenever you do these examples on the sheet, I encourage you to put them in your notes as well. Okay, so if you want examples for your notes, then put them both places. Okay, that's going to help you do the homework. Okay, so here's a little breakdown. How you're gonna state the null and alternative hypothesis, conduct the test, state your conclusion, and then also find the p-value for this particular sample. Okay, that's what I showed you before. And let's call this one number 1, okay? So it's not numbered. Call it number 1. You're free to work together. Okay, so the way this is worded, they're not saying, it's not saying our cheetah is this fast. It's just saying, they could, maybe their top speed's faster than 60, or maybe it's less than 60. So all we're going to do, and that's the clue is here, differs from. Differs from that null hypothesis would just be a two-tailed test, okay? It wouldn't be left or right. Okay, so then our z, let's do z alpha. So z alpha would actually be, for two-tailed, would be z alpha over 2. So you're going to look at, you should have looked at 0.025. And is that plus or minus 1.96? Is that right?
Yes.
Okay, so that's going to be, that sets off our rejection regions, right? If our z-score for this sample right here is less than negative 1.96, we're going to reject. And if it's greater than positive 1.96, and what are these numbers again? Negative 1.96 and 1.96? What do they mean? Number of standard deviations. So what would a z-score of 0 mean? What would a z-score of 0 mean? Yeah, that corresponds to 60 miles per hour top speed, right? It's no standard deviations away from the mean. So this is like nailing our hypothesized speed right on the head, right? 0 would be no distance away from the 60. Okay, but that's very unlikely. So what's our z-score for the test? Well, you should have done 59.526 minus. So that numerator is just how far in miles per hour we're away from our hypothesized, right? So that numerator means how far we are just in miles per hour. So we're a little bit below. But then we need to standardize that. We need to standardize that and get that into a value we can compare with z-scores. So we divide by 3.2, normalize for the size of our sample, right? And you should have gotten negative 0.88? So we'll just round to 0.88. Okay, so where does this fall in this on our scale? Do we reject or accept? No, sorry. We reject or we do not reject. Okay, so we don't accept. We either reject the null hypothesis or we do not reject it. So it's right about here. Right about here. Okay. And that's in our non-rejection region. That's in our non-rejection region. So what is our conclusion then? That the top speed of cheetahs is 60 miles per hour? Is that our conclusion? The top speed of cheetahs is 60 miles per hour. No. Remember, that's not the conclusion. What is the conclusion then? If the conclusion is we're not rejecting the null hypothesis, but what that does not mean is that we're not concluding that the mean top speed of cheetahs is 60. What is it that we're concluding? It's close to 60. Okay, that's
possible.
It's possible. So what we're concluding is we don't have enough evidence from this sample to suggest that it's not 60. That's what we're concluding. We don't have enough evidence from this particular sample at a 5% significance level that it's something other than 60. That's what it means to not reject. Not rejecting is not the same as concluding that their top speed is 60 miles per hour on average. It's just saying we don't have enough evidence to reject that. We don't have enough evidence to say that it's not 60. So we're saying it could be 60 or it could be something close. It's possible. Does that make sense? All right, so what is the p-value for a negative 0.88? What is the p-value? 18.94. And what percent is that? So when you did 18.94 in this picture, what percent are you saying is 18.94? Was that this region here?
Yes.
Okay, so how would we figure out if this is, so 18.94 is just this area over here. So what's the highest significance level? Let's see, or what's the, that we would reject, okay? So what significance level would correspond to this p-value of 18.94? What significance level? Is it an 18 point, like a 19%? Is this 19% significance? No, because it's a two-tailed test, right? Because it's a two-tailed test, you'd also have so we got negative 0.088. This is like 19, we'll just call it 19%, right? So is that the significance level? What's the significance level, actually? So then what would this area be?
19.
Also 19, right? So our significance level would be 38%. No, so what is this? Okay, so what does this mean? So this is now like we would compare this to if we were to set a significance level. If the significance level was what? Greater than this, then we would reject. And if the significance level is less than this, then we don't reject. So this is given this particular sample, at what significance level would we reject? Okay, for any significance level greater than 38%, we would reject. Right? Because if it were greater than 38%, then our cutoff would be closer in. We'd have more, the tails would be larger. we'd have closer in, and then our 0.88 would be outside of that. Okay? But if it's less than 38%, like 5% is, way less than 38%, then we do not reject. Yeah?
Wait, so if your significance level is higher and your null hypothesis is rejected, does that just mean it's like more plausible?
Yeah, the closer that your actual z-score is to the null hypothesis, the more likely it is that you're at that the mean is your hypothesized mean. Okay, so this wasn't even close, right? We weren't even getting close to the boundaries for 5%. And because of that, it's even more likely. So in order to reject this null hypothesis, we need a significance level greater than 38%, which is very, very high. Okay, which is very high. So usually our significance levels, like we've seen, are 5, 1, 10%, something like that. Okay, questions on this example?
What would be the p-value of 38%?
No, the p-value we found back here. P-value is, right, so what would be the p-value? Would it be the 38? Yeah, because it's going to be a number that we compare to alpha. Okay? So I should have said p-value. This is the p-value. And for an alpha greater than that, we'd need an alpha greater than that to reject. And remember what alpha was. It was the probability of making a type 1 error. So we need the probability of making a type 1 error, and what was that again? That we reject when we shouldn't, right? We reject when we shouldn't. We need that to be greater than 38% in order to reject the null hypothesis. Okay, questions of this example? Okay, so now here's two that you're going to do that I won't. Okay, so now it's on you. You do these two. So for both of these, so let's call this one number 2. And this one number 3. Again, you're going to state hypotheses. Let's draw a picture on these. So draw. Okay, so for 5% significance, what did you get for your z-score for 5%? This is a right-tailed test, first of all. What's the z-score for 5%? 1.645? And what z-score did you get for this sample? Quick. 3.03. Okay? So, do we reject that the average heart rate is 72 beats per minute? Right, so 0 would be 72 beats per minute. According to this sample, do we reject or not reject that the heart rate, the resting heart rate was 72 beats per minute? Reject, big time, right? Big time. And you're going to have a really super small, this is what, 5% significance, but your p-value was something really small, maybe even off the charts. You could even find it. What was your p-value? 0.01%. 1%? No. 0.12%. Is that right? Okay? So we would even reject at a 1% significance level. We'd even reject at a 0.5% significance level, right? This is way, way out here. So we would reject the hypothesis that the normal heart rate is 72. Okay, we need to go on because there's a whole other thing. It's not a lot more, but we need the time to cover it. All right? Questions on that first one? Are we good on that first one? Okay. So then, just like we talked about with confidence intervals, what about when the population standard deviation is unknown? This is kind of more of a realistic situation. You would just have a sample. You wouldn't know the population standard deviation. Okay? So everything's the same except, like we did with the confidence intervals, we're going to use the t-score rather than the z-score. Remember that when you didn't know the standard deviation of the population, you had a different type of score based on the standard deviation of the sample. But okay, so please don't work on number 2. You got to pay attention, okay? Just, if you didn't finish, we won't grade that one, okay? So number 2 won't be graded, okay? So this is now for the test where you don't know the population standard deviation. And like before, when we did confidence intervals in that situation, we use the standard deviation of the sample, and then we get the corresponding t-score, which is a different distribution than the normal distribution. Okay, but this allows us to conduct the test when we only have the sample and we don't have the standard deviation of the population. And so we use the standard deviation of the sample and a different distribution. But then besides that, it's almost the same. Okay? So let's do one of these together and you try the other one. Okay. So here we go. So the average person watched 4.55 hours of television per day in 2005. A random sample of 20 people gave the following number of hours of television watched. Okay, and so there's a table there that I omitted. So at the 10% significance level, do the data provide sufficient evidence to conclude the amount of television watched per day last year by the average person differed from that in 2005? So right-tailed, left-tailed, or two-tailed? Two-tailed. So our hypothesis is going to be that the population was, or the mean number of hours watched is what it was before, right? No, just in your notes. And then our alternative hypothesis is that the mean number of hours watched of TV is not what it used to be, right? Not what it used to be. It used to be 4.55, so we're testing for the previous mean of 4.55 hours, and now we're looking in 2005. Does it differ from that previous mean? Does it make sense? Okay, so we took a sample, and in that sample we got a mean of, we're going to need there we go. Okay, so we got a mean of what?
4.765.
Our sample in 2005 gave us a mean number of hours of 4.76 and a standard deviation of 2.297. And what was the size of our sample? 20 people. So is this going to be a z-test or a t-test? We're going to t. We don't have the standard deviation of the population, but we can calculate it for the sample. So now you're going to get a t. And remember, the t is going to be the same thing. It's going to be 4.76 minus 4.55 over 2.297 divided by the square root of 20. Okay? As soon as someone gets that, tell me what it is. 0.41. Okay? Now we want a 10% significance level, but we need to use our t-table, right? So we need to use our t-table. So you're going to go to t of what? 0.1, the column for t of 0.1. And what's our degrees of freedom? Our degrees of freedom will be always one less than the size of your sample. So you're going to go into the row df of 19. And we're going to get a number. What number do you get? 1.328. Two-tailed, thank you. Yes, she's right. So I forgot. We have a two-tailed distribution. Okay, so we do have to divide it. So what do you get when you divide it? So no, we had to divide first, right? We need 5% on either side. So we were in the wrong column. Because it's two-tailed, just like you did the z-test, your teacher just messed up. This is nothing new. We want the t of 0.05, right? And then for degrees of freedom 19, we don't want that. And so what's that? 1.729. Okay, so that means that 1.729 above would be the cutoff for rejecting, and negative 1.729 below. And what did we get? 0.41, way in here, right? Here's our 0.41. So do we reject the null hypothesis or not reject it? We do not reject. So what does that say? It says we don't have sufficient evidence to say that the mean is something other than 4.455 now compared to 2005, right? So there's not sufficient evidence to conclude some other mean of number of hours watched of 4.55. So what's different here? What's different is we're using the sample standard deviation, which means we use a different distribution. We use the t distribution, which is going to require that we know the degrees of freedom, and we use that other chart. Okay, I think we're good. Those are the only differences when you're doing the t-test. So just make sure you know in the homework, which test is it? Is it asking to compare z-scores, where you have the population standard deviation, or t-scores, where you have the sample standard deviation? Okay, so like normal, we've got homework due Sunday night. Okay?